Cardiovascular responses. Cardiac dynamics. Cardiac output is measured through the multiplication of the values for heart rate and stroke volume, meaning that if either of these numbers increase, so will the cardiac output. Heart rate is measured in beats per minute and is therefore relatively easy to calculate. Stroke volume is much more difficult to find exact values for, as it is how much blood is ejected from the heart each beat, is dependent on the heart's ability to fill and empty. These values all increase during exercise as the cardiac system responds to the increased need for oxygen and the transportation of CO2 away from the muscles. As can be seen with the table, the extent of this increase depends on the intensity of the exercise that is being undergone, as they increase much more during maximum exercise. For example, heart rate at rest would be around 70 to 72 beats per minute, whereas if you were working at maximal exercise, heart rate would be 220 minus your age to calculate the heart rate. Similarly with stroke volume, at rest it's around 60 to 80 millilitres. During maximal exercise it rises to 100 to 120. As can be seen with the heart rate chart, a small increase also happens before exercise as an anticipatory rise from the adrenaline release from the body. This could be caused by nerves or the body preparing for exercise and is only raised by a small amount, from 60 to 64 for example. However, at a point with stroke volume during submaximal exercise, the graph line plateaus as it is forced to stop increasing. This is due to the heart being unable to diastole, fill the heart with blood, in time to allow systole to happen and release the blood, which is highly important. This means that cardiac output becomes increasingly more reliant on the heart rate increasing to allow the cardiac output to raise. Heart rate is controlled by the autonomic nervous system, which therefore influences how fast contractions happen. However, it begins with receptors detecting a low level of oxygen or a high level of CO2 or lactic acid. All of these would be a cause for increased heart rate, as more oxygen needs to get to the muscles while the lactic acid and CO2 needs to be disposed. Due to this, feedback is sent to the cardiac control center in the medulla oblongata, and an impulse travels along the sympathetic nerve as heart rate needs to be increased to the SAN, which therefore sends an impulse down the heart, causing it to contract. Also, in the beginning of exercise, the parasympathetic stimulation is removed to allow the heart rate to gradually increase. This sympathetic nerve is then used as exercise increases, the sympathetic nerve is then used as exercise increases as it is an accelerator nerve and increases the heart rate even more. Blood pressure is the force that is exerted onto the walls of the blood vessels from the blood that is being transported around the body and is measured in mmHg. There are receptors inside these blood vessels called baroreceptors that are used to measure the blood pressure and detect if it is too high or low, and ultimately send signals to the brain in order to reach balance again, which is important. Blood pressure is at its highest as it leaves the heart, which is through arteries, and therefore arteries are built to withstand high blood pressure through thick muscular elastic walls that are efficient in detaining the blood inside the vessels. As a result of transporting around the body, when the blood returns to the heart in the veins, the blood pressure is much lower, and the veins do not have thick walls due to this. The equation for blood pressure is the blood flow multiplied by the resistance of the blood, and is therefore linked with the cardiac output equation, as the flow links with stroke volume, and therefore the stroke volume also affects the blood pressure. Overall, this means that if either the resistance or flow increases, so will the blood pressure, as they would both create a stronger force against the walls of the vessels, which is how it's calculated. During exercise, blood pressure is increased, as the flow is increased in order to push the blood around the body at a quicker rate, and this is detected by the baroreceptor. This will then send signals to the brain if it gets increasingly high, as it usually aims to keep balance of blood pressure. If the autonomic nervous system wants to decrease the blood pressure, it will send impulses down a parasympathetic nerve, causing vasodilation, forcing the blood vessels to widen and therefore decrease the resistance, and ultimately the blood pressure, as a resistance is a factor of this. On the other hand, if you wanted a higher blood pressure, impulses would be sent down the sympathetic nerve, causing vasoconstriction, which decreases the size of the lumen of vessels and increases resistance and blood pressure. Test results, investigation, analysis. Test results for heart rate are fairly simple to calculate, as I've said in previous slides, and we are therefore able to create a simple graph to help show the changes that happen during exercise, which can be seen in the PowerPoint. It initially starts at my resting heart rate, which is around 62 beats per minute, and pre-test it raises slightly to around 65, suggesting there was an anticipatory rise due to nerves or the body preparing for exercise. There is then a rapid increase as exercise begins, followed by a slightly more gradual increase as exercise increases and the intensity slowly rises. Once the exercise finished, it was clear I had not reached my maximum heart rate, which would be 204, as it's 220 minus 16, and the graph only reaches 146. This is my highest heart rate result, as after exercise a rapid decrease takes place as the body slows down its heart rate before a gradual decrease begins. Despite a small anomaly in the systolic reading for blood pressure, the graphs also suggest that blood pressure increased gradually throughout the test. This is likely due to my muscles' increased need for oxygen to be diffused in from the blood, which therefore created a higher blood flow, as it was trying to be transported around the body quicker, which ultimately raises the blood pressure, as it is reliant on the cardiac output. The increase in exercise may have also increased the resistance, as the force the blood would be exerting on the blood vessels be stronger and more powerful, which also has a direct effect on blood pressure. It is also important to notice that excluding the anomalies, the diastolic does not change as much during exercise compared to the systolic, which is typical for blood pressure. During a sport like football, for example, cardiac output will vary as the game progresses, depending on the intensity, tactics, and position you play. As a midfielder, it is highly likely your heart rate and stroke volume slowly increases throughout, as you'll be constantly running from box to box. It is unlikely there'll be any rapid increases, as if they are stuck to position, it is unlikely they'll need to sprint. They are also likely to have the best stamina, and therefore the highest stroke volume, and overall the highest cardiac output in a game. This differs dramatically in the role of a winger, for example, as they run a lot less than a midfielder, as they are only needed in attacking play and can relax during defending. This means at points in the match they may have the highest cardiac output, as the intensity they work at is most likely the highest due to sprinting after balls and running at fullbacks. However, overall, they do not have a high cardiac output, as they are able to rest and regain a slower heart rate and lower stroke volume at points in the match. It is also likely that a midfielder has the highest blood pressure, as they will need the fastest and longest cycle of oxygen in order to keep straining their muscles while running. This will result in a higher blood flow, and therefore more pressure, and a higher force will be exerted on the walls of the blood vessels, creating a higher blood pressure.